So we continue with the second talk of this afternoon session. So I'm very glad to introduce our second speaker, Shigui Ruan, who's going to tell us about spatial temporal dynamics in epidemic models with Levy flights.
Thank you. Happy birthday to you, Steve. Okay.
Thank you.
This is based on a paper just published in the US journal, with our former pastor, Zhao. He was here some time ago. Currently, he's at the University of Nevada. So I'm going to follow still the same line, talking about reaction diffusion, but I'm going to change a little bit. Okay? It's a fractional diffusion model. So the structure is that I'm going to give you some motivations why I studied the problem, which is kind of interesting, and then introduce the nonlocal diffusion, and then introduce the model. This is the mathematical part. So the first part may be more interesting in some sense. So because we're talking about reaction diffusion, we need to go back to know how it is started. We just start from the Brown motion. The Brown motion is about a group of particles spread as a whole according to the irregular motion of each particle. Okay. Brown observed this when in his experiments. So in 1827, he described this when he looked through a microscope at the pollen of a plant, which he was moving in the water. So that means all the particles move irregularly, but the segment, eventually the distribution is normalized. It's very nice. Okay, you can repeat that. Nobody understood that until 1905, when Einstein studied the problem. So he modeled the motion of the pollen particles as being a movement by individual water molecules. In fact, he mathematically derived this formula. He found out that suppose you have n particles at the time t equals the time when you begin in the location, and after some time, the probability distribution is given by this function. And that guy happened to be the solution of the diffusion equation. Okay, so if we said maybe we can use the heat equation to describe the Brown motion. That's how it started. Okay, this is very well-known result. So this is the probability distribution of the random walk, which is Gauss distribution. Very nice. So since then, the Laplacian operator have been used to describe many random motions, like Brown type motions, including animals and so on. Chris just gave a very nice talk. But we have to keep in mind, in Brown's original experiment, the time steps, the space steps were all small, very, very small. Basically, what he observed or what the event described was local diffusion, because the time step and also the idea, the Brown motion and the Laplacian operator have been used to describe movement in many physical biological problems, animals, plants, and so on, cells, and so on, including humans. Okay. But the natural question is that we, humans as a species, do we move randomly? This is a very serious question that's been borrowed by many people. If we do, then you use Laplacian operator to describe our movement. So in 2006, there's a very famous paper published in Nature. They were trying to study all of the mobility patterns of humans. So they, very interesting, the group of people select the 4 cities in the United States: New York, Jacksonville, a small town in Iowa, and then Seattle. What they did is they collaborated with the banks. So they initiated like more than 400,000 bank notes. Okay, so people get cash, and you remember when you go to the bank and you get cash, you usually go buy something, buy coffee or buy something from the store, and you go home. So they on each bank note there's a stick there. When you receive this note, this money, please go to the website to report your postcode. Okay. After 6 months, they received more than 1 million notes. Okay, So what do? They follow because they know where each bank knows each money was initial from the bank. They compare it, the report bank the location with the original one. They try to estimate your movement. So when we use money, usually you're very close to home or you're very close to where you work, right? So they find the estimate. Very surprisingly, that's the probability distribution, which is not a Gaussian distribution. Okay. Especially they found that, for example, for New York, almost 57% of people use the money within 10 kilometers. That's roughly what we live, right? We live, our home is probably within 10 kilometers from your place. But also there were about 7% people moving well beyond that, like 800 kilometers. Some people moving outside the country. So that you have a long tail. So this paper is very influential. It's a stunning paper. Because after that, there were more than 20 papers published in Nature. The same line. Okay? People say that, well, then you study humans, and then I can try to see how about the animals for the wandering observers from over years and years. They found that the movement of those animals follow the same pattern. And the same thing, people, another people said, well, you follow the bunch of nodes, I can trace your mobile phone, right? They found the same pattern. And the little one said, well, then how about the species in the ocean? The same thing. I thought, then let's go inside the human body. The T cells follow the same pattern. And there's another, this is interesting, this is quite interesting. So how about those hunters? So they follow a group of hunters. Most of the people hang around, talking to each other, very short distance. There's a few of them, I don't want to stick with them. I go far away, okay? And there's another people, they hired a few hundred university students in the soccer field, see how they move. Most of the people are sitting there talking, but there's a few guys go well beyond. But you always have a long tail. And there's a Levy fly. So that's a random model in which the probability distribution is heavy tail. So this kind of function is described by a constant times answer to the nature. The nature number is top. So this is the distribution. So majority are local, but you have a long tail. But the Gaussian distribution does not respect that. So surprisingly, even like this 15, several people survived more than 300 papers. There's a very large number of papers afterward. They show that Levy works appears in physics and biology, many subjects. Okay, so from those studies, we can show that the diffusion pattern of human and many other biology species are non-local. But looking back, every day when we go up, do we work randomly? No, we know where we are going, right? And maybe we just go to office. Maybe we're gonna go outside the town. Maybe we're gonna go outside the country. Then always there are some people going to other places. We're gonna cover non-local. Okay. So this is the trajectory. That is the random walk, and this is the Levy graph. Okay? Levy jump, whatever you like. So for example, you start from your home, then you go somewhere, and then you go to the office, and then you go somewhere. Then you always have long distance travel. Then how to model this kind of non-local diffusion? There's basically the two ways. The first one is called the convolution interval. So you have a convolution of that and that one. So you have interval term. The interval kernel describes the shape of that. The idea came from Kendall when he was studying the transmission of certain diseases, because usually if you're talking about diseases that are usually carried by human beings, human travel, say some people from New York come to here, and if that doesn't carry the virus or whatever, it's going to infect people all the way. So you have to consider the process. So he used a interval term to describe the diffusion. So and this also appears in the material science and so on, right? And even I wrote a survey of time ago. So there are some people study this. So that's not what I'm going to talk about. I'm going to talk about the second method, the fractional Laplacian operators. So even for fractional Laplacian operators, there's different ways to define So the first way is called the pseudo differential operators. So you have the power, you take the transform. Okay, this is the Fourier transform, Fourier approach. The second one is called hypersingular interval operators. So you consider the difference between the value at the space, and you consider difference between the two. But in the space, there are too many places. The distance is going to be close, so you have a lot of singularities. So that's why it's called super singular operator. The third one, which is the way we follow, is the semi-group approach. It's similar. So you have, say, this is your operator, and that's just each operator T is your semi-group. The semi-group acting on U minus U divided by S time 1 plus S, and you integrate and define it and divide by gamma function. So that's the semi-group. That's the gamma function. Maybe some of you know this very well, maybe some don't know where. I'll give you some idea why the Laplacian operator, fractional Laplacian operator appears. Now, you know the Levy process. You know this guy is the infinitesimal generator of the process. Very different. So if you don't know that, remember when Einstein derived the formula, he obtained the operator, the function, the delta function, there's a solution. So you use that operator. Now look at this one. You pick up a number, real number. You consider the positive and fractional x. If the guy is a positive, you take x. If the negative, you take 0. And then you define this function. This function has to be the solution of this equation. When x is less than 0 on the right hand side. So it's pretty reasonable to use this kind of operator to describe the distribution. And I showed you in the previous slides the Levy flag has a distribution function that has to the negative fraction. Okay, so that's very reasonable to use that. The study of this kind of equation is kind of new, not too long ago. The earliest papers were in the 2008 and so on. They were pretty nice journals. Cavalli and his field did a lot of work. Okay, in their books. And in fact, when Cavalli won the Appl Prize this year, when he was interviewed, this is the topic he mentioned. He was very proud of that because one of the people was cited like 1,600 times. It's very serious, very impressive. So, of course, this is a classical PDE guys. They are working on the regularity and the basic property of those equations. Well, then later on, people said, then how about I consider specific equations like the Fisher KPP equation, the logistic equation with fractional Laplacian operators. So this is a famous paper published in CMP. They found out for this kind of equation, the traveling the wave speed is much faster, exponential, very fast, very unpredictable. So there are other papers in general. And then people said, well, you study KPP, then I can study unchanged equations. And then some people even try to construct some ecological model, but just modeling without any serious mathematical modeling. So then now, going back to what is my motivation? Okay, my motivation in fact, I started looking at the problem during the outbreak of COVID. Okay. So I use this example to explain why I studied that. Now everybody knows this is Wuhan. That's where I came from. Okay. In fact, I grew up somewhere here. Okay. Wuhan, and then you have fast train to all the other cities within the province, which is in central China. Now this is Wuhan. You can see it has equal distance to the west, to Shanghai, to Beijing, to Hong Kong. This is really the center. It's a big city with 10 million people. There's more than 50 universities there. There's more than 1 million undergraduate students there. So if we had something better happen, that's ideal place. Unfortunately, that's what happened. Okay. And Wuhan has flight, before the pandemic, there's a flight to every continent in the world. Okay. Every continent, you can reach the rest of the world within 24 hours. It's a perfect location. Unfortunately, that's what happened. So when COVID started, I started farming because I came from there. That's one reason. Another reason, my wife went back to Wuhan to spend the Chinese New Year with her father, and he was stuck.
In 2020?
Yeah, was studied there. So I was looking there every day, thinking about that. So eventually, it was a lot. She was a complete lockdown. So when the United States started to show people, we are not U.S. citizens. We can have a Canadian passport. Eventually, the Canadian government, we saw like more than 200 people. So he was traveled to Toronto and was quarantined in a military base for 2 weeks, and then sent to Chicago and then back to Miami. After a long time. Okay, there's a lot of people model COVID more on the ODE sense. But you can see if you have something happen because there are people travel locally, but you have small fraction of people travel non-locally. So they travel to the rest of Wuhan, outside Wuhan very quickly, outside the province, everywhere in the country. Later on, the data shows that except Tibet, there were cases from Wuhan everywhere in the country. And there were cases travel to Italy and Spain, and then they repeat the process to the United States and other places. So this process never been modeled. So that's my motivation, to try to do something a little bit more mathematical on this way. So in other words, we think that the local movement induces spatial spread of disease within the city. Non-local movement induces the provincial, national, or international spread of the disease. That's the key. So how to model such a local and a non-local spread of infectious disease. So we started to look at it about. But interestingly, the famous paper I mentioned, the last paragraph of that paper give me some hint. Because they were able to use Levy 5 to describe the human movement. Then they said, to our knowledge, this is the first empirical evidence for such an ambivalent process in nature. We believe that this result can be served as a starting point for the development of new classes of models for human infectious diseases, because universal features of human travel can now be encountered in a quantitative way to use Levy 5. Interesting, nobody read that, or nobody followed that. Or maybe fortunately I was the one who followed it. So I think maybe this is a good idea. So during the COVID, I was reading all the Levy 5 papers and Fractional Diffusion papers. So I say that Levy 5. So this is the model. Okay. So we just considered we divide the population into two classes: those who are not infected, those are infected, right? So we indicate the density of non-infected and infected individuals at the location S at the time t. So you consider the region, of course, the region is big enough, but the boundary with smooth boundary. So you have diffusion coefficient, du for the two classes. U means susceptible, means not infected. V means susceptible. But we have a small fraction, S1, S2. Remember, they are less than 1. Okay? These are private fractions for the operator. And this is a Neumann kind of diffusion. Okay, you're not talking about diffusion. So we consider the model, which is called susceptible-infectious-susceptible model. What does that mean? So you take the probability with respect to t, that's the change rate with respect to t, and you have the diffusion. But the diffusion, you have a fraction here, that means local and non-local. This is the growth rate, or the intrinsic growth rate. This is the interspecies competition. Put them together, it's just a logistic growth. That means there's nothing happening in the population growth logistically. Okay? And that term describes the interaction between the two subgroups. So they interact each other, taking the frequency into consideration, taking the probability of transmission. Okay, so of course that's a losing term for the suspect, but it's a gain term for those people who are infected. And then for those who are infected, the same thing, but you could recover it. Suppose later on, not everybody died, most people recovered. But you could be infected again. That's, for example, COVID. Many people were second time, third time infected. So this is called a recovery term. So that's why you susceptible infection and then susceptible again. That's what SIS means. So this is just the model we're talking about. Of course, you have the region, you have the initial value, the beginning, how many people there. Of course, those values and those functions depend on the location X. So this is the model we propose. Very simple model. Okay, but we want to analyze it. Of course, you need a certain conditions, of course. One of the fraction Laplacian operator, which in fact, if you know the eigenvalues and eigenfunctions, this is the series of that, all the gamma functions defined. Okay. And we also mentioned that in if there's no disease, the probability grows logistically. And the P is the transmission rate. Q is the recovery rate. These two are the most important coefficients. The most important coefficients. And you can see we have four functions: A, B, the growth rate, the completion rate, and then the infection rate and recovery rate. So they are functions for X. So we need to put a certain assumption there. We just assume that they are wholly continuous. This contains a uniform continuous. The special case, if the two fractions S1, S2 equals 1, that's the classical reaction to gain equation, and you know how to handle it. So of course we need a certain assumptions. U is not equal, U greater than equal, not equal to 11. And this is the maximum, this is the minimum, and so on. This is very important. So if the function is L1, of course you just integrate from your domain, that's the average. This is a very important notation we're going to use. Of course, you introduce the sublimit space and introduce the bilinear forms by considering the kernel and the distance between the two values. Okay. So for the infection disease, there's a term which is called the basic reproductive number, or R0. This is a very important concept, a basic concept. All the people working in epidemiology, even Daniel's husband knows that R0. It means you have a certain disease going on. If one individual who carries a virus or bacteria, something which is spreadable, and that person comes to a naive community, then because this is spreadable, it's transmissible, and that individual is going to spread, it's going to transmit the disease to a certain number of people. Then the average number of individuals that individual will infect during his or her units is called a basic reproductive number. Think about that way. If somebody carries a virus come into the room here, if that person infects at most 1%, but that person infects at most 1%, there shouldn't be a big part. You can control it. But if that person come in, infect 2 or 3, and the next 2 or 3 people infect 2 or 3, then you can big part. So the basic reproduction is a very important concept. I always try to do it. Because that number depends on many factors. So by studying that basic reproductive number, you can propose different kind of control measures. You can see what is the best way to control that. By the way, the COVID at the first stage of in Wuhan, the basic reproductive number is 3. Okay. At the end, when China opened the door 3 years later, it was 22. So that's why within a month, the whole Chinese population was almost everybody got infected. So the virus mutate, the infection is changing dramatically. The seriousness is reduced, the death rate is low, but the infection is. That's how the virus mutate. They don't want to kill all the hosts, they just want to live with you. This way. So we want to study that. Also, we want to study the steady state or the equilibrium point. That means you let the partial with respect to time equals 0. For ordinary division, you end up solving the algebraic equation. But for reaction division, you have to handle the elliptic equation. But this one is way more complicated because you have partial fractions. Okay, so we're going to see that. We're going to study that. But before doing that, let me state the basic 2 assumptions. Very simple assumptions. Just the continuity of the 4 coefficients, A, B, P, Q. Okay, and then the average of the growth rate is greater than 0. All right. Of course, you assume that the big diversity of the population is greater. All right, the population is going to decrease. That's useful. So this is the basic assumption. So the basic real number I just mentioned to you, in fact, looks very complicated. We use the bilinear forms. Okay, involves the transmission rate, the recovery rate, and the diffusion. Okay, so this looks very complicated. In fact, it's pretty hard to analyze it. Okay, but we try to study it. But first, we try to find the upper bound, the lower bound for this guy. Okay, and interesting is that the number which has that complex formula is bounded by the average of the infection rate over the average of recovery, which makes sense. So for any disease, how many people will be infected? It really depends on how many people you are able to infect. How many of those people who recover? These are the most important factors. All the other factors are not that important. Now, if you don't consider average, you consider the ratio of these two, take the super, that's going to be your upper bound. So that's nice. You can kind of estimate the R naught. But most importantly, if you can find the principal eigenvalue of this guy, which is the you need the I here, then the sign of the principal eigenvalue is equal to the sign 1 minus R naught. Yeah, this is interesting because as I mentioned, if R naught is less than 1, you won't have disease, right? You might control. If R naught is greater than 1, you're going to have that. You'll have people infected. From the point of view of functional analysis on the reactive diffusion equation, the principal eigenvalue can tell you the stability. So this basically tells you if R naught is greater than 1, you have the equilibrium point, which is going to be stable. Because this sign is equal to 1 minus this sign of 1 minus R naught. That's interesting. So most basically we can give other kind of estimate. If the transmission rate is greater than the recovery, of course, R naught is greater than 1. That makes sense. If equal, that's only 1. If less, that's less. So that's 2. So the next one is interesting. Just you can look at it on 2 ways. The first way is the dependency of the reproductive number on the parameters we just mentioned, also the fraction, our fraction. B, remember, that's the diffusion rate. Okay? Now, if the diffusion approaches 0, that means basically nobody was moving like in the first year, everybody was stay at home. In that case, the basically reproductive number is approaching the upper bound. So you can use the upper bound to approach. In other words, if D approaches infinity, that means when you open it, okay, everybody is traveling. So the population is uniform. Okay, in that case, you use the lower bound to approximate your R naught. This one is interesting. How about the dependency on the S? S is the fraction in the operator. In that case, you need to know something about the second eigenvalue. If D times the second value is greater than 1, then this guy is non-increasing in S. Okay, well, this is the second eigenvalue. So this result looks nice, but the proof is pretty involved. In fact, we wrote another paper which is more theoretical, talking about general expression. The ideas were here. We just used the idea to this specific example. But unfortunately, this one's still not published. This is family. So then we have, then the next step is talking about the equilibrium point. You have 2 types of equilibrium point. Is that, you remember you have two components. The first component is those people who are not infected. The second is infected. So if there's nobody infected, of course, we have equilibrium non-zero, 0. That equilibrium is called a disease-free equilibrium because nobody infected. Okay, so of course, ideally you want to obtain that. So if the continuity is satisfied, the R naught is less than 1, that means every individual can infect at the most 1. In that case, it has a semi-positive equilibrium point, which is called the disease-free equilibrium. This U1 0. That's nobody infected. But the U1, of course, is the solution of the logistic equation. It makes sense. Okay. On the other hand, interesting, if the R naught becomes greater than 1 and uses this property plus, then you always have at least 1 positive equilibrium point. That means you always have certain population who are infected, certain population who are not infected. You have a positive equilibrium point. So most basically, if we consider the average, if the growth rate of average is greater than equal to the infection rate and greater than the cover, then you always have a positive equilibrium point. Okay. But then you do have a positive equilibrium. But as I mentioned, the positive equilibrium point, the steady states are the solutions that the elliptic equation with spectral power, which is not easy to find. What are you going to do? So we try to approximate, okay, in different ways. For example, we assume that du approaches 0. That means assume those who are in fact not moving. But there's no idea, but mathematically we try to consider the case. If du approaches 0, assume R naught is greater than 1, you have a positive equilibrium point, u and v. Then this sim tells you that then the positive equilibrium can be approximated by u naught and v naught. And u naught and v naught are the solutions of this equation which can be solved directly. And in other words, we cannot find the equilibrium point directly from the electric equation, but we could try to approximate when du approaches 0. Or you can do similar thing when dv approaches, which is more realistic. Like you can restrict the movement of those people who are infected if you can identify them. Let them stay home, let them stay in the hospital. You might be able to do that. The second one is more interesting. How about du approaching infinity or dv approaching the above? Okay, so you can obtain the same thing. You have positive equilibrium. When dv approaching infinity, that's the worst case. That's infected. You let them go whatever they like. So that's the most serious situation. So again, you can approximate the positive equilibrium point by the solution of this equation. The last one is even more interesting. How about we just open, just let them go. Let the du, dv both approach infinity. Let's just mean like just before the Chinese year, the year before last year, everybody did it. So the population is uniform. Okay. So in that case, the equilibrium point are constant. But the interesting part is that the density of the infected individuals is this ratio times R naught minus 1. So the R naught is very important. At the beginning, I said in Wuhan was 3, at the end, when China opened the door, was 22. That's why 90% of people infected within a month. Something like that. So now we can say something about the equilibrium point. Then as Chris talked about, so the next problem is about stability. And so this has to be a little bit careful because we are talking about reactive diffusion. You could have blow up. You have to make sure that you are able to consider the long-time behavior. So we needed to make sure the solutions do not blow up in a finite time. So we put the equations here again. We introduce some notation. Let me move fast here. So basically, we can obtain the global existence and boundaries upon the difficulty of the solution. Okay. So in fact, we need the minimum assumptions. This is the initial value when t equals 0. Okay. If the initial values are non-negative, then the problem we just considered always have a unique global positive solution. So this is nothing wrong. The solution are positive. Of course, you are talking about biological problems that have to be positive. They're globally positive. They're unique. So they make sure you can consider the stability, long-term behavior. And also, interestingly, the solutions are bounded. They do not rule out in finite time. Okay. So we try to study the stability. So we have two types of equilibrium point. The disease-free, which means not people infected, or the second one is some people are infected, some people are not infected. Two types of equilibrium point. Let's consider the long-time stability. First, the last result shows that the solution flow is bounded. It's a point is effective. So therefore, the trajectories you consider certain time in certain that's a compact. Of course, it gives a global factor. We're going to show you the global factor is exactly the equilibrium point in this case. So for the first one, this is free equilibrium point. That's U10, right? That's when R naught is less than 1. Well, we'll show you. As long as it exists, it is globally stable. We don't need the actual condition. Okay. The idea is, which is the proof in fact is long. You need the global existence point is made eigenvalues and monotone system. Why is monotone? Because the second component equals 0. You only have one equation. The one equation is logistic function, which is monotone. So you obtain all global stability. Okay. Well, the second one is space dependent. Of course, to obtain global stability of a steady state which depends on space is almost impossible. So we have to make certain assumptions. The function we just mentioned, the A, B, P, and Q are constant. Otherwise, we cannot study the global stability. Now, if they are constant, you assume that the growth rate is greater than the infection rate, is greater than the recovery. Then you have a positive equilibrium point, this one. I will show you well, this is when this is n fat, it's globally stable. And the proof is in fact very simple. You can construct the Laplace function. Only when the coefficients are constant. Otherwise, you can't do that. So we are able to propose a model and study some properties and then the dependence of certain parameters and long-term behavior. We try to do simulate because that's typical applied math. Difference. You need some simulation. So we choose the fraction numbers equal to 0.6. The diffusion Levy family. Remember, this guy appears, the power appears in the whole term. So you have 0.6 squared, and you have A and B and P and Q. Remember, this is transmission rate, this is recovery. So this one is much larger than one. Of course, you have a disease free, but you don't have too many people infected. And you can find out this guy is globally stable. Now we choose two kinds of domain. For one dimension, you choose domain from -1 to 1, and you choose the initial values. Of course, the initial value depends on the location. For the two-dimensional domain, then we just consider another two-sided function, and you can simulate that. You can see the convergence of the solution for the one dimension, the convergence in the two dimension. Okay. And you do the same thing. You only needed to change the parameters. Everything else is the same. Now, the transmission rate is 0.3, the recovery is 0.2. So this is larger than this one. Of course, you're going to have a positive equilibrium point. Of course, by our theorem, this one is globally stable. Right? So we can do the same thing. It's very standard. So I can summarize, I'm a little faster here. We talked about spread infectious disease, especially from one place to another place, especially talking about disease among the humans. So the main factor is the spatial movement, because the movement of the host, the reduce spread the disease. Okay. So the classical reaction diffusion with the Laplacian operators have been used for a long time. But I have to emphasize that those models describe the local spread, local diffusion. But there's no point I have any objection about that. I just point out factors those that the classical reaction diffusion only describes the local distribution. But for disease, we have the non-local. Especially in the modern time, we travel on many spatial scales, ranging from a few kilometers to 1,000 kilometers within a day. Especially probably the first time you heard in nature, there's a serious paper showing that the mobility pattern of the human experience a scale-free dynamics with heavy tail division. This is a character of the Levy flight. Basically, it says that 80% of people travel short distance locally, about 20% of people travel long distance, maybe middle range and long range. And the people working on epidemiology knows that this is 20% people are more risky because they spread the disease from one location to another location. Okay. So we proposed the model and studied that. One thing I have to mention here, even during the COVID, there were many restrictions about movement. They always try to stop people from the so-called risky areas to more risky areas. But for those people modeling that, in fact, they found out, well, look at this one. When we travel, who does not come back? Unless you immigrant today, or you married today, you don't come back. Most of them will come back. In fact, they found out, in fact, it's those people who travel from low-risk region to the high-risk region and return. So somehow, to our knowledge, this is the first piece of modeling by considering the Levy flight in fractional laboratories. And luckily, the two referees agreed with that. That's a kind of we didn't try to use the model to simulate any data, like from Wuhan to Nile, from New York to here and so on. I think that belongs to other people.
Were they both divorced, the referees? I'm just kidding.
So we didn't try to use the model to simulate any data. But I think that would be very interesting. I leave that to other people. So that and then I will have a high science paper again. Okay, let me stop here.
All right, thank you.